In last lecture, we have discussed about the propagation of the plane wave in lossless dielectrics. Today we will continue that to find the all parameters as we have done in previous cases when wave is propagating in free space. So let us start from here. In free space we have conductivity 0 and permittivity will be permittivity naught and mu will be mu naught. And in this case, if we wish to find the speed of the wave, then the same formula as we have done in earlier case, 1 by mu epsilon, and in case of free space, mu will be mu naught and epsilon will be epsilon naught. In free space, and if we will solve this, then we will find a well known value, that is 10 to power 8 meter per second, as it is speed. And what is this? This is speed of the plane wave in free space, and this is another known value, that is the speed of the light. So in this way we can say the plane wave propagates with the speed of the light in free space. Next thing will be intrinsic impedance in the case of free space. The formula for this is mu by epsilon. So in case of free space it will be permeability naught divided by epsilon for the free space, and both are constant, and if we try to find, then we can have 377 ohm impedance ohm, or we can write it 120 pi. Okay, so this is the impedance of the wave in free space. Impedance of wave in free space, and this is the speed of the wave in free space. Now let us try to find all the parameters that we have done in previous cases, that is gamma, alpha, beta, intrinsic impedance and loss tangent in case of the plane wave propagation, when plane wave is propagating in good conductor. So let us do that. Plane wave in good conductor. In that case, if we are choosing good conductor, then conductivity of the material will be very high. So in that case, sigma will be very high. And if we will consider perfect conductor, then for perfect conductor, sigma will be infinite for perfect conductor. We have these two knowledge, and if we have this, then we wish to find the propagation constant, attenuation constant, phase constant, intrinsic impedance and loss tangent. So as we have done in previous cases, we will try to find here as well. So let us start from the gamma. The formula of gamma is propagation constant in good conductor is just general formula without considering good conductor is j omega mu sigma plus, I think it was j omega epsilon. This was the formula to find the propagation constant. Now if we are considering the good conductor, then the conductivity will be very high And if this term is very high, it means this is much greater than omega epsilon, and if it is much greater than that, then this term can be ignored in this additive term. So the final value that we have, it will be epsilon sigma. We can write like that. Propagation constant gamma can be written as alpha plus j beta. So if we simplify this in constant and beta form, then we can have we can find the value of alpha and beta. So let us simplify this in this form. We have gamma is equal to under root j times under root omega mu epsilon, and j can be written as e to the power j pi by 2. E to the power j pi by 2 means cos pi by 2 plus j sin pi by 2. That will be only j, and this term will remain as it is. This can be written as e to the power j pi by 2 the power half omega mu epsilon. Just I am simplifying, only mathematics. So it is e to the power j pi by 4 sigma. It will be cos pi by 4 plus j sin pi by 4 plus j sin pi by 4 times sigma, and this can be written as 1 by root 2 plus j 1 by root 2. So taking 1 by root 2 outside, it will be 1 plus j omega mu and sigma. So in this way we are able to simplify this in the form of constant plus imaginary part. So further, if we simplify, then we can take this inside. That will be 1 plus j, square root is already there, so it will be mu sigma divided by 2, and further omega is 2 pi f, so that 2 and this 2 will be cancelled out. The remaining term will be 1 plus j pi f mu sigma. Now try to find alpha and beta. For that purpose, we will open the bracket. That will be pi f mu sigma plus j pi f mu sigma. Okay, what we find here, this is alpha and this is beta. So we find that alpha and beta are equal. That is for good conductor. Okay, so in this way we find the value of alpha, propagation constant, and phase constant is equal for good conductor, and this is alpha equal to beta, that is pi f mu sigma. Okay, now if we analyze this, then we find alpha is proportional to the under root sigma. From here we can say, and in case of good conductor, the conductivity is very high, and if conductivity is very high, it means alpha is very high. Okay, and if alpha is very high, it means the attenuation constant is high, and if attenuation constant is high, it means the wave amplitude will attenuate very quickly. Okay, so the more losses will be there. So we can say when wave propagates in good conductor, losses will be very high. In good conductors, losses will be very high for the wave that is propagating in that. Okay, and for perfect conductor, sigma is equal to infinity, and if sigma is equal to infinity, we can say alpha is equal to infinity. It means if alpha is very high, infinity, it means the wave equation that we have, wave amplitude that we have minus alpha if propagation is in particular direction. If it is infinite, then it will tend to 0. What it means? Amplitude is 0. It means there is no wave. Okay. In this way, we can say the electromagnetic wave cannot travel inside a good conductor. That is perfect conductor. So we can say inside a perfect conductor. Or in another way, it is very, very high for case of good conductor as well. So we can say the electromagnetic wave cannot travel inside good conductor as well. So one sentence we can write: electromagnetic wave cannot travel inside good conductor. Now let us discuss the important term, that is skin effect. We came to know that electromagnetic energy is not transmitted in the interior of a good conductor. Just we have seen it. And it travels in the region surrounding the conductor. We can say like that. There is conductor, then the electromagnetic waves that is propagating, it will not travel inside the conductor. It will be in this surrounding. We find that the time varying field attenuates very rapidly within a conductor. Now, as electric field and magnetic field, E or H, when it travels in a conductor, its amplitude attenuates, and the amplitude attenuates by a factor of e to the power minus alpha z. We have seen this. And the distance traveled by this wave, through which the amplitude decreases by a factor of e to the power minus 1, that is about 37%, is called the skin depth. In this way, when the wave amplitude decay with this factor, then the distance traveled by that wave inside the conductor is termed as the penetration depth of the medium or skin depth. So if we relate these two, then we can have E naught alpha z, original amplitude, and when it remains only e to the power minus 1. So when it remains this, then alpha z can be written as 1. From here, z is the length traveled by the wave in the conductor. So it is represented in another way, that is delta. Okay, so from here it is 1 by alpha. So skin depth is equal to the 1 by alpha. Okay, in this way we can say skin depth is the measure of the depth to which an electromagnetic wave can penetrate the medium, and for good conductors depth will be equal to the 1 by alpha, that is will be 1 by pi f mu sigma. Now if we talk about the perfect conductor, in that case the sigma will be infinite and corresponding alpha will also be infinite, and if alpha is infinite then we can have 1 by alpha, that is 0. So it means penetration of the wave is 0. So in this case we can have, for perfect conductor, wave cannot penetrate to the conductor. Okay, so wave cannot penetrate the perfect conductor. Okay, so now we will solve one example. The problem is a lossy dielectric has intrinsic impedance. The medium is lossy dielectric. And for that the intrinsic impedance is 200 with theta n is equal to 30 degree, and at a particular frequency it is propagating, and the magnetic field component of plane wave is 10 e to the power minus alpha x cos omega t minus half x. Wave propagation in the direction, the h is in the direction of ay, ampere per meter. So these are the parameters known to us in the for the wave that is propagating in the lossy dielectric. Now we have to find the first thing, that is loss tangent. Second thing is attenuation constant. Third parameter to know is skin depth, and the next parameter is the electric field from this magnetic field equation. Okay, so let us try to find all of them one by one. So we have h is equal to 10 e to the power minus alpha x cos omega t minus half, the direction of the propagation of the wave x, h component is in the direction of ay, like this we have. Now from here we find omega t minus beta x, that is the, if we relate the equation that we have, the equation of E and H, then I'm not writing that, we find that H lags E by angle theta n. Okay, so that by angle theta, not theta n, so that theta is added with this if it is lagging. So from apart from theta, beta we have here, that is half. If it is minus beta x, then it is propagating in the plus x direction. If it is plus beta x, then it means wave is propagating in the minus x direction. We have discussed this. So beta is equal to half and intrinsic impedance is equal to 230, that is given already here. Now the first parameter that we have to find, that is intrinsic impedance. No, loss tangent. So the first parameter is loss tangent, and for that we have formula for loss tangent, that is nothing tan theta, and this theta is equal to the 2 times this theta n, and that is 2 times 30. Theta is equal to 60 degree, and if theta is equal to 60 degree, then loss tangent can be written as tan 60 degree, and it will be equal to the root 3. So loss tangent, that has simple formula tan theta, and theta is nothing, just 2 times the this angle theta n, and that is 60 for this equation, for this condition, and tan 60 is equal to root 3. Now second thing is to find alpha. As we know, one relationship between alpha and beta and theta, if we recall, then that is alpha divided by beta was equal to the sec theta minus 1 divided by sec theta plus 1. Just recall, there was one formula like that. We have beta, we have theta, the only unknown parameter is alpha. So from here we can find alpha is equal to sec theta minus 1 divided by sec theta plus 1. So just put the value of known parameters, that is half theta is equal to 60 degree. So you can have sec 60 degree minus sec 60 degree plus 1. After simplification you will find it is 1 by 2 inverse 2 minus 1, that will be 2, 2 plus 1, it will be 3. So it will give you 1 by 2 root 3. So this is the value of alpha. So loss tangent is known from here. Alpha we came to know like this. Now the third is the skin effect, skin depth, that is delta, and we know the delta is nothing, just inverse of alpha. So from here we find it is 1 by 2 root 3, that will give you 2 root 3, that is the skin depth. Now the next and important thing that is required to know here is, let me erase this to save the space. It is equal to 2 root 3. Now next important parameter to find is E, and in case of E we have relationship between E and H. So following that, I am not going to write, just I am following that. E can be written as E naught minus alpha z cos omega t minus beta z, and actual H we have is equal to 10 e to the power minus alpha x cos omega t minus half x in ay direction. So if we have H, then we can find from here with the help of the intrinsic impedance. So E can be written as this times E will be intrinsic impedance times H in magnitude. So it can be written as intrinsic impedance is 200. So from there we can write 200, and remaining terms will be almost same as it was, minus half x, and here there will be one additional angle will be added here, that is theta n. If we will add it here, it will represent that magnetic field is lagging by E. So we have to present it with plus sign. And if E is leading by theta n, then it will be plus sign. We have written the formula of E, but still the direction of E is unknown. So to find the direction, let us have little bit concentration. That is, we know AE cross AH will be the direction of the propagation of the wave. That is, you can have AK, and wave is propagating in the direction of x, so we will write here AX, and AH is in the direction of AY, so AY. AE is required to know. So from here we can have for example, x, y, z is there, then the cross product of these two will give this, these two will give this, these two will give us this. So here what parameter of what should be here to give AX? So here should be minus AZ. From here we find that AE will propagate, AE will change in the direction of minus AZ. So E will be in A